Hello, and again a very warm welcome to this lecture on Permutations and Combinations Part 2. So now we know about the principles of counting, have some idea about permutations, and know what combinations are. Also we have discussed a few cases on combinations. Now it's time for us to take this topic to a next higher level. Here we are going to study about circular permutations, selection from identical objects, division of objects into groups, some important results from the study of selections, and understanding those concepts through solved examples. So students, it's time we start this lecture. So students, let's try to understand the concept of circular arrangements or circular permutations through an example. Let us take for instance, this is a wooden table and this is a circular one as well, and we have got 5 balls A, B, C, D, E arranged on the periphery of this circular table. Now the 5 balls are A, B, C, D, E and all these 5 balls are different. Now this represents the top view of the circular table, and A, B, C, D, E are arranged in the circular table in this manner. Now let us say that they start interchanging their positions this way. Now E moves to the place of A moves to the place of B moves to the place of C moves to the place of D. So what we can say is we have this second arrangement. But does this arrangement look different to you from the first arrangement? In fact, no. Both these arrangements are the same, because when we look at from this side, it seems almost the similar. Now again they start interchanging their positions this way. Now again D takes the place of E takes the place of A takes the place of B takes the place of C. Now does this arrangement seem to you different from the first or the second arrangement? No. In fact, both these three arrangements are the same. Now let's say they again interchange their position. Now does this arrangement seem different to you? No. Or does this one? No. There are actually 5 arrangements here, and all these 5 arrangements are similar. Thus we can say that a circular arrangement is very much different from a linear arrangement. Now let us see the different ways of calculating the number of circular arrangements. Let's take case number 1. The number of circular arrangements of n objects taken all at a time when anti-clockwise and clockwise arrangements are different, then it is equal to n minus 1 factorial. That is, when anti-clockwise and clockwise arrangements are different, then the number of circular arrangements of n objects taken all at a time is equal to n minus 1 factorial. Now what we are doing here is we are fixing one particular object. So how many objects we are left with? N minus 1. Now these n minus 1 objects are arranged across the fixed object in n minus 1 factorial ways. Now let's go through the second case. It says that the number of circular arrangements of n different objects taken all at a time when clockwise and anti-clockwise arrangement is not different is 1 by 2 into n minus 1 factorial. Here the important point to note is the anti-clockwise and clockwise arrangement is not different. So that is why we are dividing it by 2. So this particular thing happens in case of arrangement of beads or flowers in a necklace or a garland. So what we can say is, in the case of arrangement of beads or flowers in a necklace or a garland, the clockwise and anti-clockwise arrangement are same. That is why we divide those n minus 1 factorial ways by 2 to get the required number of ways. So let's try to solve an example to get a better understanding of what circular arrangements are. The principal of a primary school calls for a meeting of 15 teachers. In how many ways can they be seated around a circular table? If the science teacher and the Hindi teacher sits on either side of the principal, then in how many ways it is possible? So in this question, what we have is, we have a principal and 15 teachers, and they have to be seated around a circular table. So in the first part, we have to find the number of ways in which they can be seated. In the second part, it says that the science teacher and the Hindi teacher sits on either side of the principal. So again we have to find the number of ways in which it is possible, and the condition is the science teacher and the Hindi teacher sits on either side of the principal. So let's go through the solution of it. Including the principal, there are 15 teachers. So the total number of people become 16. Now we know that the number of arrangements around a circular table, or the circular arrangements of n objects where anti-clockwise and clockwise arrangements are different, is equal to n minus 1 factorial. So in this case n is equal to 16, so it becomes 16 minus 1 factorial, that is 15 factorial ways. In the second part, the condition is the Hindi teacher and the science teacher sit on either side of the principal. So let us take the principal, Hindi teacher and the science teacher as one unit or as one member. Now the total number of people become 16 minus 3 plus 1, and that is equal to 14. Now what we do is we try to arrange these 14 people or these 14 members around the circular table, and this can be done in 14 minus 1 factorial, that is equal to 13 factorial ways. Now also the Hindi teacher and the science teacher can actually be arranged in 2 factorial ways around the principal. So the total number of ways become 13 factorial into 2 factorial. Once again, in the second part, we take the principal, the Hindi teacher and the science teacher as one unit or as a one member. So the total number of people now in this case become 14. They can be arranged among themselves in 13 factorial ways. Also we see that Hindi and the science teacher can be arranged in 2 factorial ways. So the total number of ways become 13 factorial into 2 factorial. Now let us say that we have P plus Q plus R plus S objects, in which P are alike of one kind, Q are alike of other, R are alike of another, and S are different. So in this case the total number of combinations is equal to P plus 1 into Q plus 1 into R plus 1 into 2 to the power S minus 1. So here we have P plus Q plus R plus S objects in which P are alike, Q are alike, R are alike, and S are different objects. And then the total number of combinations are P plus 1 into Q plus 1 into R plus 1 into 2 to the power S minus 1. Now why does this happen is because out of P objects, P alike objects, the total number of combinations is P plus 1, as we have already discussed. For Q objects, the total combinations would be Q plus 1. Similarly for R objects, the total combinations would be R plus 1. For S different objects, the total combinations is equal to 2 to the power S. Why? Because every object in the S group has the option of getting selected or not getting selected. So it has two options. So as such there are S objects, so it becomes 2 to the power S. So the total combinations would be P plus 1 into Q plus 1 into R plus 1 into 2 to the power S. But here we want to select at least one object. So we subtract one case where none of the object has been selected. So that's why the total combinations here become P plus 1 into Q plus 1 into R plus 1 into 2 to the power S minus 1, where the case that is 0 object is selected is not included. If we want to include that case also, then we don't subtract 1 from P plus 1 into Q plus 1 into R plus 1 into 2 to the power S. Now all this time we have been discussing on the number of combinations when the things were different. But now what happens when the things become identical or they are similar? Now the number of combinations of n identical things taking k things at a time is 1. Now what does that mean? It means that if we have a group of n identical things or n identical objects and we are to select exactly k things out of those identical things, then the number of combinations is 1. Let's try to see it through an example. We can see there's a pile of balls and let us say there are n in number. Now if I ask you to select one ball, in how many ways can you do it? Now if I say I want to select this ball, then it can be done in one way. If I select this ball, it can again be done in one way. If I want to select this ball, it can be done in one way. But selection of all these balls is actually similar because the balls are similar. So the selection of balls is in one way. If I say I want to select 3 balls this time, then I can have this pair, or I can have this pair, I can have this pair, I can have this pair. But all these pairs or all these selections are actually identical because the balls are identical. Hence the number of ways of selecting 3 balls is again 1. If I want to select 7 balls, it can be done in one way. Or finally, I can say that if I want to select k balls out of n identical balls, then it can be done in only one way. Thus, the number of combinations of n identical things taking k things at a time is 1. Now, this time we are trying to find the total number of selections out of n identical things. That is, we have n identical things and we want to find the total number of ways we can select those n identical things. Now what we can say is, we can select r objects in this case, where r is equal to 0, 1, 2 up to n. Hence the total number of selections is equal to n plus 1. This is quite different from the previous case which we discussed. In that case, we were discussing about the number of selections of exactly k things out of n identical things. Here we are trying to find the total number of selections out of n identical things, and we can select r objects where r equal to 0, 1, 2 up to n. So the total number of cases become n plus 1. Let's try to visualize it and see this. What we can see is there are actually 7 cans here, and we want to select identical 7 cans. What we can do is, we have the option of selecting 0 cans, we have the option of selecting 1 can, 2 can, 3 can, or all the 7 cans. And for each of the option, the number of ways of selecting 1 can is 1, number of ways of selecting 2 cans is 2. So the total number of selections become 7 plus 1, that is equal to 8, or n plus 1. Here n is equal to 7. Thus we can say that the total number of selections out of n identical things is equal to n plus 1. Now based on the concept of total selection of n identical objects, we derive some very important results. They are, if a natural number n can be expressed as n equal to a to the power p into b to the power q into c to the power r and so on, where a, b, c are prime numbers and p, q, r are natural numbers, then the total number of divisors of n, or the total number of factors of n including 1 and the number n, is equal to p plus 1 into q plus 1 into r plus 1 and so on. If we exclude the number 1 and n, then the total number of divisors of n, or the total number of factors of n, become p plus 1 into q plus 1 into r plus 1 and so on minus 2. We subtract the two numbers 1 and n from the total number of divisors of n. Now whatever formula we have studied, that is the number of divisors of a natural number n is equal to p plus 1 into q plus 1 into r plus 1 and so on, it has been actually derived from the result on total selection or total combination for n identical objects, and that we know is equal to n plus 1. Now why? Here what we can see is that n is equal to a to the power p. Now the different powers of a could be 0, 1 up to p, and a to the power 0, a to the power 1, a to the power 2 are all factors of n. So what we see is we can select any power p from 0 to p, and here the identical objects could be taken as a. So what we have to do is we have to choose the exponent of a in p plus 1 ways. In this way the number of factors would be p plus 1 for any power of a. Similarly, when we see the exponents of b has to be chosen in q plus 1 ways, and the exponents of c can be chosen in r plus 1 ways. Thus the total number of factors is equal to p plus 1 into q plus 1 into r plus 1. Now let's look at the sum of factors of n, or the sum of divisors of n. Let us say that we can express any natural number n equal to a to the power p into b to the power q into c to the power r and so on, where a, b, c are prime numbers and p, q, r are natural numbers. Now the sum of the factors of n would be a to the power 0 plus a square up to a to the power p whole multiplied by b to the power 0 plus b square plus up to b to the power q whole multiplied by c to the power 0 plus c square plus c cube plus up to c to the power r. Now these terms are in GP. This term is in GP where the common ratio is a. This term is in another GP where the common ratio is b, and this term is also in GP where the common ratio is c. So we can write it as sum of factors of n is equal to a to the power p plus 1 minus 1 divided by a minus 1 multiplied by b to the power q plus 1 minus 1 whole divided by b minus 1 into c to the power r plus 1 minus 1 divided by c minus 1. Now the number of ways in which n can be resolved as a product of two factors. Now what we are going to do is we are trying to resolve n as a product of two factors. So that is equal to half into p plus 1 into q plus 1 into r plus 1 and so on if n is not a perfect square, and is equal to half into p plus 1 into q plus 1 into r plus 1 and so on plus 1 if n is a perfect square. Now what is a perfect square? N becomes perfect square if all the exponents of a, b and c are even, then it becomes a perfect square. If any one of the exponent is not even, is odd, then it is not a perfect square. So thus we can say that any number n can be resolved as a product of two factors in 1 by 2 into p plus 1 into q plus 1 into r plus 1 and so on if n is not a perfect square, and is equal to 1 by 2 into p plus 1 into q plus 1 into r plus 1 and so on plus 1 if n is a perfect square. Here plus 1 is inside the bracket. Thus, let's look at an example to understand what we have studied just now. Find the number of factors of the number 5 to 9 2. Also find the sum of these factors. Further, calculate the number of ways in which it can be resolved as a product of two factors. Now what we have been given is the number is 5 to 9 2, and we have to find the number of its factors. Also we have to find the sum of these factors. Further, we have to calculate the number of ways in which it can be resolved as a product of two factors. So now let's look at the solution of it. The given number is 5 to 9 2, and this can be written as 2 square into 3 cube into 7 square, where 2, 3 and 7 are prime numbers and 2, 3 and 2 are the exponents of these prime numbers. Now we know that the total number of factors would be 2 plus 1 into 3 plus 1 into 2 plus 1, that is equal to 3 into 4 into 3, that is 36. Now the total factors excluding the number would be 36 minus 1 equal to 35. If we include the number, then the total number of factors will be 36, otherwise it is 35. Now the second part is we have to find the sum of these factors. The sum of these factors would be 2 cube minus 1 by 2 minus 1 into 3 raised to power 4 minus 1 upon 3 minus 1 into 7 cube minus 1 upon 7 minus 1, and that is equal to 15960. So the sum of all these factors of the number 5 to 9 2 is equal to 15960. Now 5 to 9 2 is not a perfect square. Why? Because the power of 3 is 3 and it is an odd number. So 5 to 9 2 cannot be a perfect square. So the number of ways it can be resolved as a product of two factors is equal to 1 by 2 into 2 plus 1 into 3 plus 1 into 2 plus 1, and that is equal to 18. Once again what we have done is we have the number 5292 and we have expressed it as 2 square into 3 cube into 7 square. So the number of total factors equal to 2 plus 1 into 3 plus 1 into 2 plus 1, where 2, 3 and 2 are the exponents of the numbers 2, 3 and 7 respectively. So that equals to 36. The sum of these factors is equal to 2 cube minus 1 upon 2 minus 1 into 3 raised to power 4 minus 1 divided by 3 minus 1 into 7 cube minus 1 divided by 7 minus 1, and that is equal to 15960. 5292 is not a perfect square, so it can be resolved as product of two factors in the way 1 by 2 into 2 plus 1 into 3 plus 1 into 2 plus 1, and that is equal to 18. Now let's move on to the next major part of this lecture, that is the division of objects into groups. Here the objects are not identical but they are different, and what we have to do is we have to divide them into groups. So the number of ways in which m plus n different things can be divided into two groups which contain m and n things respectively is m plus n cm into n cn, and that is equal to m plus n factorial divided by m factorial into n factorial. Now why it is so? We have been given that there are m plus n different things. Now we have to divide them into two groups which contain m and n things respectively. So what we do is, first we select m things out of those m plus n things, and this can be done in m plus n cm number of ways. Now we are left with n things and we have to select n things out of those n things. That could be done in n cn number of ways. Now when we multiply both these m plus n cm into n cn, that is equal to m plus n factorial divided by m factorial into n factorial. Similarly, if the number of things be m plus n plus p and they are all different, so the number of ways in which they can be divided into three groups containing m, n and p things is m plus n plus p cm into n plus p cn into p cp, and that is equal to m plus n plus p factorial divided by m factorial into n factorial into p factorial. So what we are doing here is, we have m plus n plus p different things and they have to be divided into groups containing m, n and p things. So what we do first is, we select m things out of this group of m plus n plus p, and that can be done in m plus n plus p cm number of ways. Now we are left with n plus p things, and out of those n plus p things we select n things. This can be done in n plus p cn. Now what we are left with is p things, so we select p things out of those p things. When we multiply all them, we get m plus n plus p whole factorial divided by m factorial n factorial p factorial. Now let's study the division of objects into equal groups. That is, the number of objects in different groups is equal. Now there are actually two cases of this. First, the order of groups is not important, and second, order of groups is important. Let us say that we have got 2m different objects and they have to be divided into two groups. That is, they have to be equally divided into two groups. So each group would contain m objects. So there are two groups containing m and m objects. So this can be done in 2m factorial divided by 2 factorial into m factorial whole square. Now this is very much similar to the previous case which we have studied. Here the difference is m is equal to n. So the total number of objects become 2m and each of the group contains m objects. But the difference here is that it is divided by 2 factorial term. This is because the two groups have equal number of elements, so they cannot be arranged among themselves. So that is why it has been divided by 2 factorial. The second case is, order of groups is important. Here the arrangement is very much important. So for 2m different objects to be divided equally into two groups, the number of ways is equal to 2m factorial divided by 2 factorial into m factorial whole square multiplied by 2 factorial. This part is actually equal to this part, but the only difference is it is being multiplied by 2 factorial. And why we are multiplying it with 2 factorial? Because the arrangement of groups is important in this case. That is, the order of groups is important. So we can arrange them in 2 factorial ways. So the total number of ways would be 2m factorial divided by 2 factorial into m factorial whole square multiplied by 2 factorial. So on similar lines, we can say that the number of ways in which m into n different things can be divided equally into m groups is, when order of group is not important, in that case m into n factorial divided by n factorial to the power m into m factorial. Why? Because we are dividing m into n different things into m groups. So each group contains n objects. So when we write the formula, we get as m into n factorial divided by n factorial to the power m divided by m factorial. The second case is when the order of group is important. Here what we do is we just multiply this with m factorial, that is the number of groups. So it becomes m into n factorial divided by n factorial to the power m into m factorial whole multiplied by m factorial. Let's go through a solved example to understand the concept of division of objects into groups. In how many ways can we distribute 10 different chocolates among 3 boys so that one boy receives 5 chocolates, other receives 2 chocolates and the other receives 3 chocolates? Also find the number of ways of dividing these chocolates into groups of 5, 2 and 3. So what we have been given is, we have got 10 chocolates and they have to be distributed among 3 boys, so that the first receives 5 chocolates, the second receives 2 chocolates and the third receives 3 chocolates. Also in the second case, we have to just divide these chocolates into groups of 5, 2 and 3. So let's see the solution of it. Here in the first part, we have to distribute the chocolates to 3 boys. The number of chocolates is equal to 10 and the number of boys is equal to 3. So the arrangement of these groups is very much important. First we divide these chocolates into 3 groups containing 5, 3 and 2 chocolates, and then we arrange them in 3 factorial ways. So the number of ways equal to 10 factorial divided by 5 factorial into 3 factorial into 2 factorial whole multiplied by 3 factorial. 3 factorial we have multiplied it with because the arrangement of these groups is very important. In the second case, or in the second part, we have to divide the chocolates in 3 groups. Here the order is not to be considered. So what we can say is the number of ways is equal to 10 factorial whole divided by 5 factorial into 3 factorial into 2 factorial. So students, let's try to solve an IIT JEE problem that appeared in 1979. In how many ways can a pack of 52 cards be A. divided equally among 4 players in order, B. divided into 4 groups of 13 cards each, and C. divided in 4 sets, 3 of them having 17 cards each and the 4th just 1 card? So what we have to do in this question is, we have a pack of 52 cards. Now in the first part, we have to divide these 52 cards equally among 4 players in order. In the second part, we have to divide these 52 cards into 4 groups each containing 13 cards, and in C part we have to divide these 52 cards into 4 sets, and 3 of them have 17 cards and the 4th just 1 card. Now let's find out the number of ways in which n different things can be arranged in r different groups. Here all the n things are different and they have to be arranged in r different groups, but it is not given that which group contains how many objects. So it is done in n plus r minus 1 pn if blank groups are allowed, and n factorial into n minus 1 cr minus 1 if blank groups are not allowed. That is, the groups cannot have 0 objects or 0 elements. Thus we can say that the number of ways in which n different things can be arranged in r different groups is n plus r minus 1 pn if blank groups are allowed, and n factorial into n minus 1 cr minus 1 if blank groups are not allowed. Let's solve an example based on the above formula. There are 6 different balls and they have to be arranged in 4 different boxes so that no box remains empty. Then find the number of ways in which they can be arranged. So in this problem we have been given 6 different balls and they have to be arranged in 4 different boxes. The condition here is that no box should remain empty. So we have to find the number of ways in which they can be arranged. Now we can do this problem from the above formula which we have discussed. But we are going to try it through another approach. We are going to try to visualize this problem and solve it through combinations. Now the 4 boxes can be this way. We have been given 6 balls. So what can be the combination is, one box can contain one ball, one box can contain again one ball, the third box can also contain one ball, and the fourth one can contain 3 balls. Now we can write it in a table form that box A can contain one ball, box B can contain one ball, box C can contain again one ball, and box D can contain 3 balls. But these boxes, the balls and the boxes can be arranged among themselves. So the boxes can be arranged in 4 factorial by 3 factorial ways, and of these arrangements the balls can also be arranged in 6 factorial ways among themselves. So the number of ways is equal to 6 factorial into 4 factorial divided by 3 factorial, and that is equal to 6 factorial into 4. Now the other case could be, one box contains one ball, second box contains one ball, third box contains 2 balls, and the fourth box contains again 2 balls. This can be written in tabular form as, box A contains one ball, box B contains one ball, box C contains 2 balls, and box D contains again 2 balls. The balls can be put in the boxes in this way. Also the boxes can be arranged in 4 factorial by 2 factorial into 2 factorial ways. So like box A can contain 2 balls, box B can contain 2 balls, box C contains 1 balls, and box D contains 1 balls. So in this way there are different combinations. Now again the balls can be arranged among themselves in 6 factorial ways. So the number of ways is equal to 6 factorial into 4 factorial by 2 factorial into 2 factorial is equal to 6 factorial into 6. Thus we can say that the total number of combinations is the sum of the number of ways obtained from both the cases, that is 6 factorial into 4 plus 6 factorial into 6, and that is equal to 6 factorial into 10. Now 6 factorial is equal to 720 into 10 is equal to 7200. So these are the number of ways in which the 6 balls can be arranged in 3 different boxes.